Welcome to the deep dive. Today, we're jumping into something truly foundational, something that literally changed how we see reality itself. We're talking about Albert Einstein's theory of relativity.
Right, a massive topic.
It really is. You probably know it came in two parts, special relativity around 1905, and then general relativity about 10 years later, 1915.
Yep.
But the thing is, these theories did more than just explain stuff. They fundamentally redefined space, time, gravity, everything. So our mission today is to sort of unpack these huge ideas and show you just how connected they are to, well, everything you see when you look up at the night sky. Their impact on astronomy is just staggering.
Absolutely. And it's key to remember, this isn't just, abstract math on a blackboard somewhere. It's the actual toolkit we use to understand the cosmos.
Right.
From, tiny high-speed particles hitting Earth all the way up to the biggest structures in the universe. So yeah, we'll look at what the theories say, but maybe more importantly, why astronomers absolutely need them to make sense of it all.
Okay, great. So where do we start? Special relativity, 1905. Einstein basically said, imagine two things are true. First, the laws of physics work the same for everybody who's moving smoothly, constant speed, straight lines.
Seems reasonable enough. Standard idea, really.
Right. But then comes the second bit, and this is the one that just blows your mind. The speed of light in a vacuum is always the same for everyone, no matter how fast you're moving towards it or away from it.
Yeah, that's the kicker. It doesn't add up like throwing a ball from a moving train.
Yeah.
Light speed is just constant, full stop.
And accepting that has some really weird consequences for our everyday ideas about time and space, doesn't it?
Oh, absolutely. It completely unravels them. You get things like time dilation.
Okay, what's that?
Basically, moving clocks tick slower than stationary ones. Time isn't universal. It actually depends on how fast you're moving. So like the famous example, if you flew off in a super fast spaceship close to light speed, time would genuinely pass slower for you than for someone back on Earth. You'd age less.
That is just wild to think about. Really messes with your head.
It does. And then there's length contraction. Objects moving really, really fast appear shorter in their direction of motion, at least to an outside observer.
So things get shorter and time slows down.
And the big one, probably the most famous equation ever. Eve, see it, mass energy equivalence.
Energy equals mass times the speed of light squared.
Exactly. It means mass and energy are, interchangeable. A tiny amount of mass holds an enormous amount of energy. It's what powers stars, nuclear reactions. It's fundamental.
Okay, so these are mind-bending ideas, but how do we actually see them playing out in astronomy?
Well, take cosmic rays. These are particles, protons and stuff, zipping through space incredibly fast, hitting our atmosphere. Many of them are unstable. They should decay, break down way before they reach us.
But they don't.
They don't, because they're moving so close to the speed of light, time dilation kicks in. From their perspective, hardly any time passes on their journey here.
Wow, so we can detect them because of relativity.
Pretty much, yeah. Without it, they wouldn't make it. And think about pulsars. These super dense, spinning neutron stars. They send out these beams of radiation like cosmic lighthouses with incredibly precise timing.
Like clocks, right?
Exactly. But to use them as accurate clocks, astronomers have to factor in all these relativistic effects. Their speed, their strong gravity. Special relativity is essential for interpreting those signals correctly.
Okay, so that's special relativity, handling constant motion and light speed. But then Einstein tackled gravity.
Right, that was general relativity, 1915. He realized special relativity didn't account for acceleration or gravity. So he took it a step further. And his big insight here was that gravity isn't a force pulling things together like Newton thought.
Not a pull. Then what is it?
It's the curvature, the bending of space-time itself. Mass and energy actually warp the fabric of space and time around them.
Okay, hang on. Fabric of space-time.
Yeah, think of it like, the classic analogy, a stretched rubber sheet, put a heavy ball like a bowling ball on it, it creates a dip, a curve. Now, if you roll a little marble nearby, it doesn't get magically pulled by the bowling ball. It just follows the curve in the sheet caused by the bowling ball.
Ah, I see. So massive things like planets and stars create curves in this space-time fabric.
Exactly. A four-dimensional fabric, 3 of space, 1 of time. And other objects, even light, just follow the curves. What we feel as gravity is just us moving along these warps.
Okay, that's a big shift in thinking. What are the consequences of that?
Well, just like speed affects time in special relativity, gravity affects time in general relativity. That's gravitational time dilation. Time actually runs slower closer to a massive object.
Yeah.
So a clock on the surface of Earth ticks just a tiny bit slower than a clock on a satellite orbiting higher up.
Seriously, it's a measurable difference.
Oh yeah, absolutely measurable. And crucial, as we'll
Yeah.
see. Then there's the paths objects take. They follow the straightest possible lines through this curved space-time. We call these geodesics.
So even light bends when it passes near something massive because it's following the curve.
Precisely. It's not being pulled, it's just following the geometry of space-time. And maybe the most dramatic prediction, gravitational waves. If massive objects accelerate, like two black holes spiraling into each other and merging, they should create ripples in the space-time fabric itself, spreading outwards like waves on a pond.
We've detected those now, right? LIGO?
We have a huge confirmation of Einstein's theory a century later. Amazing stuff.
So, connecting this to astronomy, general relativity explains some really major things then.
Oh, absolutely fundamental things, like black holes. These are where space-time is warped so extremely by gravity that nothing, not even light, can escape once it crosses the event horizon. Time slows down incredibly near a black hole from an outside perspective. It's the ultimate expression of warped space-time.
And the bending of light you mentioned, that's gravitational lensing, isn't it?
Exactly. Massive objects like galaxies or galaxy clusters act like lenses, bending the light from objects behind them.
So we can see things that are hidden.
We can. It magnifies and distorts the images of distant galaxies, letting us see things we wouldn't otherwise. And it's even become a key tool for mapping out dark matter.
How does that work?
Because dark matter doesn't emit light, but it does have mass, so it curves space-time. We can see its gravitational lensing effect on background light, even though we can't see the matter itself.
Clever. And wasn't there something about Mercury's orbit?
Yes, that was a huge early success for general relativity.
Mm-hmm.
Newton's theory couldn't quite explain this tiny wobble, this precession, in Mercury's orbit around the Sun. But Einstein's theory, accounting for the Sun's warping of spacetime near it, predicted the orbit perfectly. It was compelling evidence.
Okay, this is all fascinating cosmic stuff, but you mentioned something about it being practical.
Ah, yes, the perfect example. GPS satellites.
Yeah.
Your phone, your car's navigation,
Hmm.
they rely on signals from satellites orbiting Earth.
Right.
Well, those satellites are moving fast, so special relativity says their clocks should tick slightly slower than clocks on Earth.
Okay, time dilation due to speed.
But they're also farther away from Earth's gravity, so general relativity says their clocks should tick slightly faster than clocks on Earth.
Ah, gravitational time dilation. So you have both effects.
You have both, and they don't cancel out perfectly. To get the pinpoint accuracy we need for GPS, you have to precisely calculate and correct for both relativistic effects. Without Einstein's theories, your GPS would be off by several miles within a single day. It just wouldn't work.
Wow. Okay, that really brings it home. It's not just theory, it's in our pockets.
Exactly. It underpins so much of modern tech and, of course, modern astronomy. We've touched on some examples, but relativity is just woven into everything. Understanding black holes, vital for galaxy evolution studies and gravitational wave sources, gravitational lensing for seeing the distant universe and probing dark matter, the expansion of the universe itself. General relativity predicts a dynamic, changing space-time, which is the foundation of cosmology.
So the Big Bang model relies on it.
Fundamentally, yes. And studying things like neutron stars, these incredibly dense objects, are like natural laboratories for testing general relativity under extreme conditions. Even measuring the mass of distant stars and galaxies often relies on gravitational redshift.
What's that?
It's related to time dilation. Light escaping a strong gravitational field loses energy, shifting its wavelength towards the red end of the spectrum. Measuring that shift tells you about the strength of the gravity and thus the mass of the object.
It's incredible how these concepts just keep popping up everywhere. The math must be pretty intense, though.
Oh, the math gets very complex, yes. Scientists use specific tools, equations like the Lorentz factor for special relativity effects, or the equations for gravitational time dilation, to make these precise calculations.
But the point is, these aren't just abstract ideas anymore. They make concrete, testable predictions that match what we observe.
Exactly. That's why relativity is so crucial. Summing it up, you really can't do modern astronomy without it. Predicting black hole behavior, planning deep space missions accurately, understanding how the universe evolved, interpreting telescope data. It's all built on Einstein's insights.
It really is the language the cosmos speaks.
Well put.
So, as we wrap up this deep dive, it's just kind of staggering to think about. A little over 100 years ago, these were radical, abstract ideas. And now, they're the absolute bedrock of how we understand the universe. For you listening, it means our universe is way more flexible, more dynamic, more interconnected than we ever thought. And our grasp of it, even things like GPS, leans entirely on these incredible counterintuitive insights about space and time.
It really does. And, something to maybe mull over is how we keep testing and confirming these ideas. Think about the effort that went into Eddington's 1919 eclipse observation, showing starlight bending around the sun. Or the sheer technological marvel of LIGO, actually hearing black holes merge through gravitational waves. It makes you wonder, doesn't it, given that relativity itself underpins our model of the Big Bang and cosmic expansion? What other fundamental truths about our reality might be hiding? What other forces or maybe even dimensions are shaping things in ways we're only just starting to glimpse, just waiting for that next breakthrough?